Hello guys, today we're going to be talking about algorithms. This is the introduction to algorithms. And as I stated, other than tutoring you, I'll just be giving you questions and answers based on how I know or how I think questions are going to be asked, right? So you may be asked to give a one-word problem. What is an algorithm for starters? Oh, it's off. What is an algorithm for starters? Well, an algorithm is an ordered set of unambiguous executable instructions that define the terminating process. From the top of my head, I can remember that, and I did mention it. So, algorithms are just an ordered set of unambiguous executable instructions that define a terminating process. You can say a termination process in other words. So let me just highlight these other words, these words. The algorithm has to be ordered. It has to have unambiguous and executable instructions that define a terminating process. Now let's start by terminating. When we talk about terminating, we mean that this thing should come to an end, right? Whatsoever you're defining, whatsoever algorithm you are defining, it should terminate, it should come to an end. Now, for executable, the steps should actually gives you the desired result. I can't say that I'm making a function that adds two numbers and then it multiplies those two numbers. It won't be giving me the desired results, right? Number three, it has to be unambiguous, meaning that each step must state exactly what is required. Then the ordered part just means that the algorithm is well established, the structure is readable, everything is in an ordered way. Okay, so if they ask you what are the steps in an algorithm that must have a well established structure, then you can just say it's an ordered it's an ordered whatsoever. Then if it's about stating, then it's unambiguous, then it's about giving results, it's executable, and if it's about ending, it's terminating, in other words. Okay, now an algorithm has a representation which requires a well-defined primitive or well-defined primitives, and those collections of primitives constitute a programming languages I mean a programming language. Sorry, I'll just write that down. Well, before I write that down, let me just uh, take these things and write them in a way that you understand. So now the steps in an algorithm that must have that must have oh that have a well established. Did I say established? Yes, I think I did say established. Well established. That have a well established structure means that it's ordered already. It's ordered, right? If something has a well established structure, it means that it is ordered. And if something gives you exactly what is required, then it's unambiguous. Ambiguous means that something is not clear. So unambiguous means that it's clear. It's actually giving you what is required. So if the steps state exactly what is required, means that it's unambiguous. How is it? I don't even know how ambiguous is spelled, so you're just going to bear with me with this. Now, the other part is that if the steps give you the desired results, that means it is executable. Your algorithm, on the other hand, is executable. Steps give desired results, means that it is executable. Okay, and then if your algorithm leads to an end, then it is terminatable, or that's termination. All right, if your algo goes to conclusion or it ends, that it's called termination. Well, terminating. Okay, then there are ways to define an algorithm. Well, not to define, but to represent an algorithm, which is primitives. And those primitives make up a programming language. You should know that from the top of your head. All right. It is actually represented by a well structured primitives, right? So it should be having well structured primitives. And primitives make up a programming language. And by make up a programming language, I mean that a collection just constitutes. Now let's move on to pseudocode. Pseudocode is a generic way of describing or defining an algorithm without the syntax or the use of a programming language. Right? Pseudo code. It's just a fake way of coding. Now it is just a generic way of describing or defining an algorithm without any specific syntax. Of a programming language. Now let's actually recap for some small time. Okay, now as I mentioned, an algorithm is an ordered set of unambiguous executable instructions that define a terminating process or a termination process. It's up to you to how you define it, but make sure that the things that I highlighted are actually in the definition that you're going to make up on yourself or by yourself in the process. Algorithms are ordered sets of unambiguous executable instructions that define a termination process. This may come in your quiz, as he stated that he just picks whatsoever questions that you get are just picked in a random pool. We don't get the same questions We may, but the chances of us getting the same questions are low, right? Now, an algorithm has steps or definitions. Okay, these are definitions right here. All right. So when you define an algorithm has to be ordered, right? The algorithm has to be ordered, in which what the ordered part means is that the steps are well established. They have a good structure, right? The second definition is that it has to be unambiguous, meaning that it shouldn't be unclear or whatsoever that you're writing. It has to has something that confuses other people. You know, you can write a code which only you can maintain, and if only you can maintain that code, that means that the other people cannot actually work with you because they don't know how it works. So something that is unambiguous means that it is readable. It does exactly, or it states exactly what is required. Exactly. Now, the other definition is that it has to be executable. And to be executable, it means that it should give the desired results. Whatsoever that you want it to do, it should do that without any errors. And the final one, it has to be terminating, meaning that your algorithm goes to conclusion. It must lead to an end. I forgot to write or lead to end. Sorry. Which color was I using? Colorblind. Has to reach conclusion or leads to end. Right? Those are the four basic, or those are the four definitions of an algorithm that you need to know. Then again, we have representations of algorithms or of an algorithm. The first one is that an algorithm requires a well-defined primitive or well-defined primitives, right? By well-defined, we mean that it has to be well-structured. Let me write well-defined. It has to be well-defined primitives. And primitives constitute a programming language, meaning that a collection of primitives, man, I can't even spell, a collection of primitives make up a programming language. Right? Then the other part is pseudocode, which is a generic way of describing or defining an algorithm without any specific syntax of a programming language. Now, after this, we have assignments, which I will do. After this part, I will show you how assignments work. We have the if condition or a conditional selection. Okay, you have to know what they are called. The conditional selection is that you have two options, and one option should meet your requirements. Okay, well, the option that you have meets your requirement, or if it doesn't, then whatsoever. If you find something that you want in the shop, you are going to take it, right? Yes, that's it. The second one, it's if again. If you find something in the shop, but it's not what you want, then you're going to do something else. Maybe you're going to leave the shop or get an alternative, or get that as an alternative. All right. So if a condition is met, then do that. If it's not met, then do the other thing. Okay. Then number two, we have repeated executions, in which it's the while loop and the do while loop. But in terms of algorithms, we say the while and the repeat. Okay. So while the condition is true, do the activity. And the do while, which is called the repeat, is that repeat the activity until the condition is true. Okay. Then for the third one, I think we have only three. primitives, which is a procedure. In my own understanding, a procedure is a function. Maybe you say void menu, inside the parentheses you give the menu a name. Well, because it's a void function, we'll leave those things out of there. Okay. uh, so a procedure just says procedure name parentheses generic names. All right. That's a function in my own understanding. So let me just note them down for you. So we have the pseudocode primitives, pseudo primitives. All right, in which one we have the conditional. What is it called? I'm selecting two things here. Conditional selection. In conditional selections, we have the if. All right, it's only the if. If this is it, then do it. If the condition is met, then action, that just do whatsoever that is there. The second one is that if a condition is not met, if condition is not met, well, I'm sorry for that. If a condition is met, right? If a condition is met, then run the first thing. Else, if it's not met, run the second thing. Maybe I'm saying that if age is less than 18, then just write something like hello whatsoever. Else, just write sorry about that. No, or something like that. So the second one just states this: if condition, then action 1. Else, if the condition is not met, then action 2. You're just choosing between two things. Maybe they have an equal value or not, but you're just choosing between two things. Then we have the repeat execution, or repeated execution, if I may say, repeated execution, whereby we have a while a condition is true, then you should do an activity. On the while or the repeated execution, I can actually give you a practical example, which I won't write down. Let's say, while you're not tired, go take a walk, right? While you are still fresh, or while you just woke up, go take a bath, whatsoever that is. And then we have a repeat. We say repeat activity until you meet a condition. Now here we repeat an activity until a condition is met. Meaning what? You are going to keep on walking or jogging until you get tired, right? You're going to go on cooking until the food is ready, or it's I don't even know what it's called when the food is ready, and I can't say ripe because ripe is for fruits. So yeah, we keep waiting for the fruits until they are ripe so that we can eat them. It's a repeat condition. Then we have the procedure, in which it's just a procedure. Then you give it a name, and in parentheses you just give generic names. All right. That's actually how these ones work. And then after this we have iterative structures. Okay. And after iterative structures, I think we're going to have components of repetitive control. Okay. So let's go to uh, iterative structures. Iter. Okay. Iterative structure, whereby we have a pretest. Well, I'm going to talk about postfix and prefix notations or whatsoever in the C++ part. This one just describes whatsoever that I'm going to tell you then. All right. So number one, we have a pretest. Oh no, you can't die on me now. We have a pretest. We have a pretest loop, whereby we first check the condition and then we loop the body. The while loop is a great example. While a condition is true, then you do or you execute the body. You do loop the body. Body. Right. Then after the pre-test loop, we have the post-test loop, whereby it's a do-while loop in some other case, like I said, whereby you repeat the loop body until a condition is met. Okay, that's how it is. Now let's move on to the repetitive control. Components of repetitive control. It's such a long word. Now, the components of repetitive control, whereby I call them item, not item, but item, ITM, whereby you initialize, then you test, then lastly there has to be modification. Looks like I wrote mad. Then there's modification. By initializing, we just give an initial state that will be modified towards termination, and when we test, we compare the current state to the termination. Let me just write a practical example. Right, so we're initializing, let's say x. Oh no, I have to write in pseudo. Okay, let's say x is 1, right? And the termination, maybe let's say y is 5, right? This is initializing, right? We initialized x and y. Now we have to test these things, right? Let's say we want to terminate the whatsoever we have when it reaches 5 or when it goes over 5, 1 over 5, right? We're going to say while, is that how you spell while? Okay, while x is actually less than y, right? We do say x plus 1. Okay, well, this is not how you write it actually. You say x will be equal to x plus 1, right? Now it's going to iterate through. This is testing, the testing part. Is x greater than y? No. Then, okay, I think, let me just not erase this. Let me just put it down here actually. While x is less than y, print x. Okay, now while x is less than y, let's print x. Now in this part, let me just write whatsoever. Okay, is y greater than x? No. Well, actually, I'm saying it in a wrong way. Is x greater than y? No. Then let's print x. It's 1. Then x is equal to x plus 1. So now x will be equal to 2. Now x is 2. Is 2 greater than 5? No. Print 2. Then x is equal to x plus 1, which is going to be 3. Now, is 3 greater than 5? No. Then we print x, blah, 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 4. Then it's 4 greater than 5? No. Then we go on. Now, is 5 greater than 5? No. Then x now is 6. Now, is 6 greater than 5? Yes. Then now we're not going to print x. We're just going to terminate the algorithm. So this is where it ends. It ends at 5. This is a pre-test loop, okay? So now, the modification part. What we've done is the test and modify. The test just checks or compares the current state with the termination condition. And the modification just changes the state in a way that it moves towards the termination condition. And when it reaches the termination condition, of course, it's going to stop, right? Great. Now, this is how the ITM is. The item whereby it's initialize, test, and modify. Well, we use a Z actually. I forget about that. And modify. Right. So initialize, test, and modify. Okay. We initialize, we test, and then we modify. Well, this is the modification right here. Right. We initialize, test, and modify. That's that. After that, we have how loop structures are and the repeat loop structure is, right? So let me pass on. Now we have a control structure. I don't know if I will get the definition right. Okay, but in my sense, a control structure is something that alters the what do you call it? It alters the execution of an algorithm or a sequence of program. It alters the execution of a sequence of a program. I don't know if I got it right, but you'll find it somewhere. Well, before I go there again, let me go back and make sure that you are actually getting this. Okay. Pseudocode primitives, right? We have a conditional selection. We have a repeating or a repetitive. I forgot the name. Repetitive loop. Yes, repetitive loop. And then we have the procedure, right? Now, in the conditional selection, as I mentioned, you just choose between two options. I will go in the control structures or control statements. All right. So the condition selection is if. If something is true, then you do this. If it's false, then you do this. That. Then we have the repeated execution, whereby we have a while loop and a do while loop. Okay. Now, if you are asked which condition just does the activity, it does an activity when a condition is true. It's the while loop. Which one does an activity until a condition is true? It's the repeat. Okay. Yes, that. Then we have the procedure. I don't actually know how this one works, but in my own case, it's a function, just like void menu, and then like this. Or maybe you are trying to do something double. You are adding something like A1 and A2. These are the generic names in here. All right. Now we move to the iterative structures, whereby we have a pretest and a post-test loop. All right. The pretest loop says that while a condition is true, you loop over the body. I did explain, right? And now a post-test loop repeats the loop body until the condition is met. All right. That's actually how it is. You have to know these things by heart, because you're going to be using it in almost each and every programming language. So if they ask you in interviews, maybe they would ask you how, well, no, write a pseudocode that will define this, or maybe code using the given pseudocode. So you're just going to be knowing this, right? Now, the components of repetitive control. Why did I write control? Control, repetitive control, whereby we have an ITM, whereby we initialize, test, and modify throughout the whole algorithm body. Okay, now we have a control statement which just executes, right? It executes the sequence of a program, just like that. Okay, control statement or control structures. Control structures or control statements, whereby it's just execution an execution of sequence. Oh, no. I knew that I was forgetting something. It alters the execution. I saw that it wasn't making sense. Execution of sequence of program. Of a program. It alters the execution sequence of a program. Yes, of a program. I'm not doing English as my major. Now we have the go-to statement. In the control structure, we have the go-to statement in which it just directs the execution to the other location. Right? What directs the execution sequence to another location? It's the go-to statement. Okay, that's how questions may be asked, or how a question may be asked. The go-to statement just directs the execution no, not the execution of, the execution sequence to another location. All right. That's the go-to statement. It directs the execution sequence to another location. Now, the second one, we have the if then else statement. If then else. Where is it? This one right here. The if then else. This thing is so slow to go down. Hey, number 2, we have the if then else statement, which just gives you a choice between two options. It's just choosing between two options. This is not easy to remember. All of this that I'm actually giving you right now is not easy to remember, but I'll make sure that you understand, right? I'll do my best for you to understand. And if you don't understand, you can just text me and state where you are not understanding it. You know those things. Then a similar statement. We have the case statement, whereby here the only difference is that you are choosing between a lot of options. You can use if, else if, but it's going to be messy and not going to be readable. So it's going to be easier to use the case statement. All right. Now number 4 is number 4. We have the go to, then we have the if then else, then case yes. Number 4, we have the while statement, whereby you just allow the body to be executed if the condition is true. All right, you allow the body to be executed if the condition is true. All right, and those are all the things that you need to know. Pseudocode, I think you're going to have to study it. Well, no, let me help you out with pseudocode. Okay. I'll use, if I still remember correctly, I'll use Mr. Malachi's example. I think the word was science. Right. And the question just says design a pseudocode which counts vowels, if I do remember correctly. So when you are designing a pseudocode to write, let me write that down. Design a pseudocode, pseudo code that counts vowels. For pseudocode, I'd actually recommend you to go to pseudocode editor. It's browser based. You don't need to install it. The one that runs on laptops or PCs or whatsoever, I think they are actually hard to implement because pseudocode just requires you to have a pen and a paper and a brain, of course, right? So when we're designing, we need to think about the steps that we can take or the steps that we can make. Well, number 1, we have a letter here. Letter number 1, we can initialize it, right? Like we can call it a current letter. we are initializing right now, which is going to be 1, right? Now, number 2, read and identify the vowels, meaning that you are going to repeat the process until the last letter is read, all right? In which here is the last letter. We're going to repeat the process until the last letter, which is 1, 2, 3, 4, 5, 6, 7. 7. And the last part, I think we're going to increment. What do you call it when we are count? Oh yes, it's counting. Then we're going to increase a count by 1 each and every time. So our count is to be 0 every time we start a code, right? Now, because it's this, we're going to repeat the loop, all right? So I'm going to say repeat. Repeat this thing when the condition is that the current letter is actually less than the last letter. All right. Well, actually, no. Wait. We first read. Let me just take this to the bottom. We first read a letter. All right. Now, the first thing we do is just read a letter. It's going to be a repeat statement, whereby number 1, we read a letter. Then, if the letter is a vowel, I think I can erase that now. Now, if a letter is a vowel, I like using parentheses to actually make my things clear. Now, if the letter is a vowel, then you increase the count. Then count is going to be count plus 1, right? And then current letter. Okay, this is where it goes. It gets confusing, all right? The if statement works with the then. There is no else. In this specific case, there is no else. Okay, so we are just going to leave a white space. Aibo, there's no white. Okay, we're just going to leave a white space here. Okay, so that you don't confuse yourselves. Even here, there's a white space. We leave white spaces so that there's readability. You have to leave white spaces whenever you are writing your code, right? I just wanted to get that off because it confuses, right? Then when you read the current letter, when you read a letter, the current letter is just going to be iterated by 1. You can use an equal sign. It's best to use an equal sign. This is just a demonstration, right? So it's going to be a current letter plus 1. Okay, and we are going to repeat this until until a condition is met. Until current letter is greater than last letter. The moment current letter goes to 8, then you're going to terminate your process. This can be shown in this table. I think it's called a trace table. Okay, let me draw it. Black 0.2. Then we have the current letter. Then we have the last letter. we have the count. Then we have, what do we call it? Wait, let me check. We have the current letter, we have the last letter, we have the count. Then we repeat, we read the letter, right? Oh yes, we read the letter. Then is a letter a vowel? Yes or no. You just say yes, then no. Then the last one is the current letter. Aiwo, come on, stylus. Current letter greater than last letter. Yes or no, maybe true or false. This is a Boolean. This is a Boolean question. So it's true or false. Okay, now we have the current letter. We have the count of current letter. Here it is 1. It's initialized to 1, right? So it's 1, 2, 3, 4, 5, 6, 7, 8. Okay, now the last letter we initialized it to 7. So it's 7 throughout. 7, 7, 7, 7, 7. Now the letters are signs. Science. All right. Now the count is still at 0 because we initialized it to 0 right here. Okay. Now we have the letter S. Is the letter S a vowel? Well, no, it's not a vowel. Okay. Then our count is going to increase by 1, as we stated here. Okay. If letter is a vowel, then count is going to be count plus 1. Okay, that's my mistake actually. That's actually my mistake. I'm sorry about that. Count is going to be 0 because our letter is not a vowel. Now, the current letter is 1 and the last letter is 7. So is the current letter bigger than the last letter? No, it's false. We're not going to do that. We're not going to terminate now. Then we go to letter number 2. Letter number 2 is a C. Is a C a vowel? No. Then our count is going to still remain as 0. Then here we have a false because 1 is still less than 7. Number 3, letter number 3, we have an I. Is the letter a vowel? Well, yes. Now, according to our statement, if the letter is a vowel, we take count and add 1. We say count equal to count plus 1. So 0 plus 1 is just going to be 1. Okay. So the current letter still is less than 7. Well, not greater than 7. I meant not greater than 7 because if I say less than 7, then that means if it reaches 7, it's going to terminate. So the current letter is still less than 7. Okay. Now, science. Oh, this is an E. Okay, I thought it was a G. Then now let's go to letter number 4. An E. Is an E a vowel? Yes, an E is a vowel. The count now is 1. We say count equal to count plus 1. So 2. Now, is 5 greater than 7? No, 5 is not greater than 7, so we're not going to terminate it. Let's go to letter number 5, which is an N. Is an N a vowel? No. So our count is just going to remain as 2. Sorry about that. And still, 5 is not greater than 7. Then 6, we have a C. Is a C a vowel? No. Then we have a 2 still, and still false here because a 6 is not greater than 7. Now number 7, we have an E. Is the letter E a vowel? Yes. Now let's say count plus 1. 3. Is 7 greater than 7? No, 7 is not greater than 7. Now the last letter, there's no last letter. and count is at 8. Is 8 greater than 7? Well, yes, now we're going to terminate our process in step 8. All right. But, okay, but let me actually go back up here. All right. We say current letter equals to current letter plus 1. So here, it's going to be 2. The current letter after this is 2, 3, 4, 5, 6, 7, 8. The moment it passes 7, it's going to be a true statement, meaning that we won't go to 8 as there's nothing associated with 8 right here. There are no letters anymore. So it's just going to terminate after it iterates to 8. The moment it says 8, it's going to stop. All right. You repeat the body until something happens. The moment the current letter says 8, termination, the algorithm terminates. Okay. Now, there's something called the polia. Uh, I think you'll look for it. Polia. Polia. Problem solving steps. In which one you have to understand the problem. You can't solve a problem that you don't understand, can you? One, you have to understand the problem. Number two, you have to make a plan to solve the problem. Number three, you carry out the plan. And then number four, which is the last one, you evaluate. What are we evaluating? Evaluate. You evaluate the solution for accuracy and potential. You evaluate the solution for accuracy. Oh, and its potential. Its potential as a tool for solving other problems. This is exactly how it is. All right. I think this is where we're going to end for now. Okay. We'll do the outputs. This is where I'm ending for the theory part. So now we're going to be doing the programming part. Okay. But I'll do it in a separate video, but I'll upload them at the same time. Okay. So after this video, just go and watch the part where I'm actually explaining the pseudocode in real coding. Thanks. Have a nice day or nice night, wherever you are, or whatsoever time I upload this video. Cheers.